So what we're going to do in episode 2 here for target 10.1 is go ahead and talk more about what are the parts of a confidence interval. Again, remember from episode 1, a confidence interval is some point estimate we get from a sample plus or minus the margin of error, where the margin of error is found by some critical value times the standard error. And according to the central limit theorem, the standard error is basically your population standard deviation divided by the square root of your sample size. In other words, it's the value of the standard deviation of a sampling distribution of sample means. Okay? I know that's a little tongue twister. I got tongue twisted myself, but again, the standard error is just basically the value of a standard deviation or spread for a sampling distribution of sample means. Now, when we construct a confidence interval, we look first of all at the confidence level. The confidence level, again, is the probability, or it could be a percentage, such as 0.95 or 95%, that the interval actually contains the population parameter, in this case, the population mean. And this is important, assuming that process, that estimation process, is repeated a large number of times. So basically what we're saying for a confidence level of 95%, we're saying if we construct 100 confidence intervals, then we feel approximately 95% of them should contain the true population mean. We can't guarantee that it will, that our interval does contain the population mean. The only way you can do that is sample the entire population. So we'll talk more about this in a little bit. But this value, this alpha, written as, again, Greek letter alpha, that tends to be the complement of the confidence level. So confidence level is equal to 1 minus alpha. Now, we'll talk more about alpha when we get into, when we start talking about hypothesis testing for standard 11. But here are some very common confidence levels: 90%, 95%, and 99%. And of course, the confidence level can be anything you want it to be, but those are the 3 most common. And then you can see their corresponding levels of alpha. Now, again, I wouldn't get too hung up on knowing alpha right now, but we will once we start talking more about hypothesis testing in the next standard. Now, as we said before, a confidence interval starts with a point estimate. That again is the value you get from taking a sample that is used to estimate the population parameter. In other words, that would be, for instance, if we're dealing with trying to estimate a population mean mu, then the best point estimate would be the sample mean we get from a sample, x bar, okay? So again, a point estimate is just a single value, okay? It's a statistic. In other words, the sample mean in this case that we use to estimate the population. We don't know how good it is. That's why we create an interval. It could be very good. It could be a very good indicator of the population mean, or it could not be. So again, our confidence intervals start with this idea of a point estimate. Now, the other part of it was the critical value. And basically the critical value is the number of standard errors that, to move away from the mean of a sampling distribution, that correspond to a specific level of confidence. Now, it's very similar to when we talked about z-score. Remember, a z-score was the number of standard deviation a value was away from the mean. Well, a critical value is the number of standard errors, which again, remember, were the standard deviation of a sampling distribution. And it is based on, ladies and gentlemen, your level of confidence. Now, the thing is, because our sample size vary, we're not going to look at a standard normal distribution or a z-score. We're going to actually let our critical values be denoted by something called a t-distribution, which looks very much like, in most cases, a z-distribution. And you can go on your Art of Stat app to see that there is a t-distribution. And I'm going to go through again what a t-distribution means, or what it looks like, and how we use it to construct confidence intervals. Because you can either use, there are tables that we used to use, which I don't think we should use anymore, but we can use technology to figure out what these critical values are. Now, the thing is, if we're trying to estimate the population mean, we very rarely know the population standard deviation, sigma, okay? So again, a student t-distribution is based off of the idea that we do not know what the population population standard deviation is. And it's called a student t-distribution, but generally we just short it up and call it a t-distribution. So what I'm going to do here is I'm going to show you how a t-distribution looks very normal, looks unimodal and symmetric, but it tends to vary from a standard normal distribution that we've been looking at. So I'm going to go ahead and pause this for a second. So I went ahead and paused it, or you can too, and you can go ahead and go back to your like I said, your ArtiStat app and do this with me. Go to your t-distribution, and then what we're going to do is we're going to explore what a t-distribution looks like. So I'm going to click to the next screen, and I'm going to go right here. Now, t-distributions are based off of something called a degree of freedom, and all a degree of freedom is a sample size minus 1. Now I'm going to show the standard normal curve. Notice how our t-distribution is green is a little bit wider, it's not as tall, and it's a little bit more, the tails tend to be a little thicker. But notice as I increase the degrees of freedom, how the t-distribution approaches that standard normal distribution in blue. In other words, ladies and gentlemen, the larger my degrees of freedom, which is a sample size minus 1, the closer it gets to that standard normal distribution. It gets a little bit taller, thinner, and the tails get narrower. Now, on episode 3, we're going to do a little bit more of explaining about this t-distribution, and we're going to look at something called the standard error.